Hello, today I am going to give a presentation about our career proceeding entitled THERMO-SHADING. My name is Jungwon Yoon from University of Seoul. Here is a brief introduction and a list of recently published journal articles. These proceedings and all the sources used for this presentation are outcomes of the research project, a study on a sustainable energy efficient envelope applying thermal-responsive smart materials conducted from 2017 till February of 2020. This proceeding paper is a subsequent to the article entitled Design to Fabrication with Thermal-Responsive Shape Memory Polymer Application for Building Skins, published in Architectural Science Review this year, as well as the conference proceeding Additive Manufacturing of SMP for Deployable Structures, presented in 2019. Also, it is concurrent with the paper Performance Evaluation and Design of Thermal-Responsive SMP Shading Prototypes, published in May 2020. The project started from the timely interest on climate adaptive responsive facades combining solar shading with material-based actuated system in SMP. The basic principle is to apply SMP to the transformative shape-changing part if the temperature rises above the specifically transition temperature, the SMP becomes pliable and deformable to recover its pre-programmed shape. The pre-programmed shape is trained during the manufacturing process. In kicking off the project, we started the case studies of responsive facade design and categorized the examples into 4 types. The representative examples of 4 types were interpreted into SMP elements and experimented for 3D printing and behavioral tests. Of a number of prototypes, this study targets to focus on design and fabrication of SMP with a flapping mechanism resulted from blending wings. The first prototype is called as blade, referenced from flecked fin. The second prototype is one of deployable prototypes in various complicated geometries. The selected type named SWIRL is a radial arrangement of the 4 bending wings from blade. The design was selected due to its simplicity and one's directionality in reversing the closed shape into open positions. Therefore, 2 designs are discussed for the design to fabrication process and empirical and reiterative experiments. In the process, the experimental results make us revisit the fabrication and design, while SMP material types also require recalibrations and procedural modifications. For rapid manufacturing and prompt feedback between design and fabrication, 3D printing was undertaken to fabricate SMP components. Cubicon single plus was used in our experiments. SMP with different class transition temperature were tested for 3D printing. Also, the filament manufacturing process with SMP pellets was involved. Additionally, enlarging the printing size was another challenge to take. In the early stage of additive manufacturing, the commercial available filament in MM5520 was used. To achieve more responsive SMP components in the real temperature conditions, MM3520 and MM2520 were tested for 3D printing after making the custom filaments. Additionally, to verify the efficiency of 3D printing by comparing different manufacturing methods for SMP, casting was also experimented. Casting is proceeded in 4 steps. First, mold production, second, solution preparation, third, casting, and lastly, drying and curing. In mold production, 3D printing was also applied to make ABS molds as well as to make ABS masters for silicon molds. In solution preparation, its resin and hardener should be dried for 1 hour at less than 50 torr before being mixed by stirring for 30 seconds and 60 RPM and being patted to the mold. From now on, I will share the design and manufacturing processes and results per type. First, blade. From our experiments, it was noted that the thickness along the bending axis would affect the behavioral performance and mechanical properties of the SMP model. Therefore, the type 2 was determined to test the thickness along the axis. Type 3 was designed to test the influence of curvature along the bending axis upon the SMP deformation and responses. As a result, the default type 1 was easier to be 3D printed but weaker at the bending area. Type 2 was a version of a spine addition to Type 1. In case of a Type 3, the curvature was added in the opposite direction from the bending direction. You can see the picture of a Type 1 model made of MM5520. In 3D printing, Type 2 and 3, printing direction and support setting were important factors determined for the successful fabrication. It took 1 hour and 20 minutes for Type 2 and 4 hours for Type 3 to complete the 3D printing. In heat test, Type 2 showed the successful transition between programming and shape changing. However, Type 3 showed problems in recovering the shape. Therefore, for the further 3D printing test in MM3520, Type 2 was selected. The table shows the different 3D printing setting as per the glass transition temperature. In 3D printing with the MM3520, many recalibration processes were taken to achieve the successful setting. Also, in heat test, the MM3520 showed much more prompt response to the temperature and quicker shape changing. From this experiment, we can secure the 3D printing setting of our 3D printer for MM3520. For the more complicated type SWIRL, we also conducted a series of trials for 3D printing. Due to viscosity of a hot melt SMP and sensitivity of the printer, the process was halted in many times. However, by human handling actions to prevent the SMP clog in the nozzle and recognition errors against the filament, the final production could be accomplished. However, in scaling up the model size from 100 mm to 150 mm, previously unknown matters stood out. After failure in 3D printing, the design model was reviewed and fixed. To verify the 3D printability of the form, ABS and TPU were applied for 3D printing of the same model. But due to the SMP material properties, 3D printability was completely different from others. There are several issues to tackle, which include mounting method of the model to the bed plate, replacement of support materials to other solid and hard materials, replacement of the 3D printer machine, and the review of filament thickness and flow amounts from the nozzle. Without resolving problems by human surveillance and support, it takes 10 hours to print the 150 mm model, which is not desirable in rapid prototyping. With the concern and doubt on 3D printing, we conducted SMP resin casting experiments. Molds were made in 2 different materials and processes. However, the SMP resin models made of silicon mold showed problems. Due to the volume of the prototype, the curing time for SMP increased significantly from the guided duration up to 3 days. Also, the complicated geometry was turned out as not adequate for casting. From experiments with the 2 different manufacturing methods, although the 3D printing was difficult to conduct for SMP models, it was demonstrated that 3D printing is superior to casting from its advantage of production time, required equipment, procedure, and consumed materials. This comparison informed us to revisit the system and the SMP design. SWIRL was designed simply as the surface-active system, but in consideration of reversibility of the shape and complications in fabrication, the prototype was redesigned to have an SMP actuator with other flexible surface materials. As shown in figures, the system was more divided into elements to utilize the material-based actuator and the simple mechanical control to program and revert the shape changing. The designed SMP actuators were simple and easy to be 3D printed, but this again throws a question on the effectiveness and appropriateness of the design outcome and the manufacturing method. Nevertheless, throughout the whole process from blade to SWIRL, from surface active to actuator system, the last prototype was the design which achieved the desired size and kinetic movements. From the series of experiments and research, we could demonstrate shape changing and reversibility of MM3520 prototypes, which makes it convincing to apply MM3520 to a climate-adaptive building skin. However, we still need a better solution for reverse programming. Besides, the performance and environmental effects of shading elements should be validated by simulations and mock-up tests. We also could review selection of fabrication methods rather than blind pursuit of the 3D printing. From this study, we could check many challenges to overcome. The limitations of current 3D printers should be resolved to tackle fundamental 3D printing issues. Also, the shape of the prototype should be carefully considered to take advantages of 3D printing. In addition, the scale of the 3D printed components should be cared for optimization of time and effort. Therefore, it is rational to consider design optimization, which can be best suitable for 3D printing without missing the design intent and concept. Lastly, to make the full-scale components or an installation using SMP elements, it is necessary to consider the assembly. Differently from the fabrication study of single components, joints, and connectors are critical. Let me conclude this presentation by summarizing our findings. We presented a bottom-up approach toward thermal-responsive smart materials and climate-adaptive facades by focusing on very specific forms and mechanisms, as well as by experimenting and understanding the SMP additive manufacturing. The final assembly, which is a kit of parts, presents a promising shape-changing behavior and deploying performance. However, form-finding approach may mislead the design direction. Rather, it is helpful to rethink and revisit the SMP prototype shapes and behaviors as well as mechanisms after fabrication tests. To further develop the SMP prototypes, it is needed to examine composite systems and assembly of SMP other materials. This research was supported by the National Research Fund of Korea. Thank you for your time.